Okay, so module 9.2, we're going to now deal with hypothesis testing with proportions. We're going to have to make sure we check all of our conditions, conduct the test, and then construct a confidence interval, and or just find the p-value here. Okay. Oops. All right. So 9.1, it had the significance test and the idea of a p-value. So now we're going to test the details of a claim when we are dealing with proportions, basically. And we're going to have one-sided and two-sided tests. So if you remember, one-sided is just when one tail, we're looking at the area of just one tail, and two-sided, we have the area of both tails going on. All right, so carrying out a significance test, if you can think back to 9.1, we had the basketball player who claimed to have an 80% free throw average. So in an simple random sample of 50 free throws, and he made 32. So his sample proportion of made shots was 32 out of 50, which was 0.64. So we want to know, does this provide convincing evidence against his claim? So to find out, we must perform a significance test. So we're going to set up our hypothesis. So remember, this guy can only be population variables, and P is the proportion for the population. And then over here, we're going to put the population as well. For both of them, they're always the same. You always have an equal sign going on in the null. And in this case, we are thinking that it is less than because we got 0.64. So we're testing to see if it's less than. So don't forget, you're going to have to check all of your conditions. We have our conditions. We have to have it random. We have to have normal. So if we're dealing with proportions, then we have n times p. And in this case, it's going to be 40, and n times 1 minus p, which is 10. And both are greater than or equal to 10. So the normal here is met. And the random, it said it was an SRS. And then the independence, we're going to check that 10% rule, or you can say the outcome of each shot is not determined by determined by a random number generator here. So individual observations are independent. One shot does not affect the next shot. All right, so carrying out the significance test. So we're going to find our mean and our standard deviation. So if you recall, the mean in a proportion is just the p itself, which was 0.8. And the standard deviation here for sigma sub p hat, so the sample here going on for the standard deviation, we're going to use p times 1 minus p over n, and that gets to be roughly 0.0566. So if I set it up in a normal density curve going on, we have our mean in the middle at 0.8, and then you can see approximately where your p hat's going to lie. Okay, so it's 0.64 or less would all be that area in the tail. So this is going to be a one-sided. All right, so we're going to have a test statistic to measure how far a sample statistic diverges from what we would expect the null hypothesis if it were true in standardized units. So you can always go back to convert to Z. So you can convert what you had, 0.64. If you remember, this is your statistic minus your parameter over your standard deviation. You can see that this has a z-score of negative 0.283. Gosh, you are almost 3 standard deviations away from the mean. That is going to be really rare. Okay? And that's on your formula sheet if you want to make sure you know your z-scores. So here we could look at this. This was our original. We were looking for that area. Or we could make it normalized with our z. Remember, the mean is always 1, or sorry, the mean is always 0 and standard deviations are always 1. And we had a negative 2.83. So those would fall like in the same spots going on that density curve if you wanted to just put it in a normal, a standardized. sorry, a standardized density curve. So that shaded area we could find doing the p-value. And we could have the p-value is less than or equal when z is negative 2.83. Okay, but you do not have to always convert it back to z's. You could have just did the normal CDF from negative infinity to that 0.64, and then in this case we had a mean of 0.8 and a standard deviation of 0.0566. But if you use the normal CDF with the z's, your mean was 0, your standard deviation was 1. You don't ever have to write those in. It will assume those if you're in z's, but you'll get the same answer if you do write them in. Okay, so when I went and did this, I got 0.00235. Well, what do you know? It's the same answer. So it's up to you if you like converting it back to z's and always remembering that formula, but you do not have to if you're in a time crunch. So if the null is true and the player really does make 80% of his free throws, in the long run there's only about a 0.23% chance that the player would make as few as 32 out of 50 shots. So what does this mean? That's a really small chance, okay? So I don't think that, let me go back here. So that's a really small chance. So here your p-value was 0.0023. Remember when we talked about in 9.1, that's definitely smaller than even 0.01 at the 99% confidence interval. So I definitely think we have enough here to reject the null, okay? Now, when you do those normal CDFs, don't forget this is not enough work just to write a normal CDF. You have to say the area under the density curve with a mean of blank and a standard deviation of blank from blank to blank would be 0.0023. So make sure you definitely would state all of that as we've talked about before. Okay? Or you could show the labeled curve on the AP exam, and that is full credit too. All right, so we're going to do the one sample z-test, kind of what we were just doing, but now we're going to say exactly what we should be doing. So what's our hypothesis, and what test are we going to use? Okay, and if you use symbols in your hypothesis, make sure you always define what those symbols represent. Okay. So get your hypothesis, define the variables, and make sure you say what test you're going to use. Then check your conditions. So check all three conditions, random, normal, independent. And then if the conditions are met, perform the calculations. Compute the test statistic, find the p-value, and then interpret the results in context. Make sure it's always in context of the problem. Okay? So when all your conditions are met, then you can say it's going to be approximately normal. You have a mean and a standard deviation, what we saw before. Okay, so if you like converting it to z's, you can always use the z formula. So you could have your statistic, which would be p hat, minus your parameter p all over your standard deviation. Okay? Okay. So use this test only when the expected numbers of successes and failures are both at least 10, right? We cannot perform unless it is normal. So we can do a one proportion z-test instead of the interval here. So if I'm calculating the p-value, I'm doing a test. If I'm calculating an interval, then it'd be a one proportion z interval. You could also check all of this in your calculator. So here you're going to put in what you get out for, so what is, so here this is what the claim is, okay? So that's what they're saying for that population. That's going to be in your null. And then your X out of the N is how many you, like basically how many trials you have. So that was like the 47 out of 50. Okay. So X is the number of successes. And then go pick whichever one, get it highlighted, whichever one you're looking at. And then you can hit calculate. You could also see what draw does. It goes in on your computer or on your calculator and the graphing screen, and it shows a nice little density curve. So definitely look around at that. Here you could see when I put all of that in, this would be my outputs. So here I can see that would be the Z value going on, but here is the P that I'm looking for. Okay. Here it tells you what P hat is if you didn't already have that. But you could calculate that pretty easy. And here you can see when you did hit draw, that's the area you're looking for. Make sure it matches up with what you have, or you probably put something in wrong. Okay, so why you can use your calculator on the AP exam. There's a risk involved. If all you do is give the calculator answer with no work, you will probably get no credit. Okay, so make sure you are just kind of checking it with your calculator. That would be my biggest suggestion, and always draw out your labeled density curve. Okay, so let's get to our example. 1 potato, 2 potato, 3 potato, 4. A potato chip producer has just received a truckload of potatoes from its main supplier. If the producer determines that more than 8% of the potatoes in the shipment have blemishes, the truck will be sent away to get another load from the supplier. A supervisor selects a random sample of 500 potatoes from the truck, and an inspector reveals that 47 have blemishes. Carry out a significance test at alpha equals 0.10. So here we're doing 90% confidence. What should the producer conclude? So we've seen this a little bit. Let's see if we can first state your hypothesis, what all your variables represent, and what test you're going to be using. So here my hypothesis is going to be P equals 0.08. And here we are wanting to know if it is bigger than 0.08, because that's when we're going to send it away. All right, so then you actually have to tell me what P is going to be. P is the actual proportion of potatoes in the shipment with blemishes. So you could either write that in here, or you could just say that P equals this. All right. And the test we're going to use, we are dealing with a one sample z-test for the population proportion. So one sample z-test for the population proportion. Now we need to check our conditions. Was it random? So yes, they told me that they did a random sample. So it was stated in words. Selects a random sample. Is it normal? Well, let's check our n times p and our n times 1 minus p. Both are greater than 10, greater than or equal to 10, so we are good. It is normal. And now independent. Because we are sampling without replacement, we need to check the 10% condition. So if you are sampling and you're replacing, then those are independent. But this is not independent. After you take out one, then you have, like, things are changing. So as long as you check that 10% condition, you'll be okay. So let's see, 10 times our sample of 500 is 5,000, and there are at least 5,000 potatoes in the shipment is what we need to be assuming. So that seems like a reasonable assumption. So if you like converting it to the z-score I'm showing you, I don't like to do this very much, but go for it if this is your thing. So you can convert your statistic minus your parameter divided by your standard deviation, and this gives you a z of about 1.15. Otherwise, you could set up your density curve here. Let's see, our mean instead was 0.08. Oops, no. Yeah, 0.08. And we are looking 47 out of 500. I need my calculator. Hold on. So that's 0.094. So we are looking for that area. All right, so both of those would be great. So we could do a normal CDF using the z-scores, or you could go and look at the table A, what that z-value in the table represents. But what I'm going to do is this right here, okay? And I'm going to state what I'm doing or have that drawn in. So I'm going to say the area under the density curve from 0.094 to infinity with a mean of 0.08 and a standard deviation of this guy right here is equal to, and what is that equal to? 0.12426. All right, so our p-value now, we're going to see what's going on. We're going to compare it to our alpha that they told us, the significance level of 0.10, and we're looking at our p-value, and it is bigger. So 0.12426 is greater than the 0.10, so it is not statistically significant here. Okay? So there is not sufficient evidence to conclude that the shipment contains more than 8% blemished potatoes. So the producer is going to use that truckload to make his fries, or potato chips, sorry, potato chips. All right, so this is what I was talking about. You could use it just this way. This is how I like to set it up, okay? But be careful about always using the normal CDF, that you are either drawing out this density curve or you're explaining what you're going to do. Okay, so now what if you have a two-sided test? What's that going to look like? So let's read this one. According to the Centers for Disease Control and Prevention website, 50% of high school students have never smoked a cigarette. Taeyeon wonders whether this national result holds true in his large urban high school. For his AP Statistics class project, Taeyeon surveys an SRS, so a simple random sample of 150 students from his school. He gets responses from all 150 students, and 90 say that they have never smoked a cigarette. What should Taeyeon conclude? Give appropriate evidence to support your answer. All right, so let's set up our hypothesis test, define our variables, and say what test we're going to use. So here, we're going to have that P, which P represents the actual or the population proportion of students in his school who have never smoked the cigarette. So we're saying that P is equal to the 0.5. So we always have in the equals here, and then it says, gets responses, and let's see, wonder whether this result holds true. So results hold true doesn't mean it's greater than or less than, it just means it would not be equal to when you see results hold true. Okay, so that's what we're going to put in, and I know when it's not equal to, we're going to have a two-sided sample going on now. So in this case, we have a one sample z-test for the population proportion. We're going to check our conditions. Said it was random. Let's see if it's normal. N times P, N times 1 minus P, both are greater than or equal to 10, so we're good. And independent, so since we're sampling without a replacement here, we're going to check our 10% condition. So 10 times 150, I say that there are at least 1,500 students if it's a large urban high school. All right, so again, if you like to do the Z, I'm not going to focus on that as much because, I don't know, I just don't always convert it to Z's as much. Okay, so here if you had this, you could put where the Z's would be located. But I see that our sample proportion is 6.6, so I'm actually going to draw out, said that it was 0.5, so I'm looking at 0.6. Okay, and we're going to have the equal amount on the other side. You always just kind of go symmetrical here. So that would be the density curve if you don't like to convert to Z's. So here with mine, I'm going to do my normal CDF from 0.6 to infinity. And that's only going to give me this half of it though. So I'm going to have to take that, and since it's symmetrical, and multiply it by 2. So you have to multiply it by 2 when you have two-sided, and that would be my p-value. And again, since I'm using a normal CDF, I either have to have my drawing or explain what everything means in that normal CDF. Okay, so now that I have my p-value, 0.0143 is less than 0.05. The alpha that he chose to go with, because that's, if it doesn't say, that's the one you usually pick. Okay, so this is statistically significant, and we have sufficient evidence to reject the null hypothesis and conclude that the portion of students at Taeyeon's school who would say that they have never smoked differs from the national results. We don't know if it's less than or bigger than, but we know it's different. So this is kind of what I was showing you that I would do. Okay. You could definitely put this into your calculator. Just be careful when you're putting it into your calculator to find that p-value. That is completely fine. This is actually, instead of the normal CDF, you could definitely do your one proportion z-test in your calculator. And then you just have to conclude. But again, make sure that you're drawing out or explaining what you're doing when you're using the calculator. Okay, so we had confidence intervals going on in Module 8, and now we're doing the hypothesis testing in Module 9. So which one's better? So the result of a significance test is basically a decision to either reject the null or fail to reject the null. So when we reject the null hypothesis, we're left wondering, well, hey, what is the actual proportion? So a confidence interval could help us out here. So if I found the confidence interval for Taeyeon's here, found that 90 of the 150 students said they had never smoked a cigarette, then we could see a little bit of where we feel it would actually fall. So here, let me just show you. Okay, so if you constructed this confidence interval, you could see that at his school, you would be 95% confident that it would fall between 0.522 and 0.678. So before on that last one, we didn't even know if it was higher or lower. We just know that it was different. Okay, so we failed to reject. Here, a confidence interval is going to give us a little bit more information to show us where it is approximately. Okay. So since 0.5, oh, you can't see that. 0.5 is not included. Then again, you could reject the null hypothesis now, okay? Because it is not included in that 95% confidence interval. So you're going to get the same outputs for either rejecting or failing to reject. But here you could definitely reject the null because 0.5 is not included. Okay. So here, confidence interval with two-sided tests. There's a link between confidence interval and two-sided tests. The 95% confidence interval gives an approximate range of p-naughts that would be rejected by a two-sided test at your significance level. The link isn't perfect because the standard error used for the confidence interval is based on the sample proportion, while the denominator of the test statistic is based on the value of p-naught from the hypothesis. So if you'd like to know this, great, but otherwise you've kind of already got the basics down. Okay, and I'll let you read through that. So here's our summary. And we are going to do 9.3 next. So basically it's the exact same thing, but now instead of dealing with proportions, we're going to deal with means.